Hello, dear viewer. I'm glad to see you on this video. Make yourself comfortable. I'll play music with certain frequencies that are known to have a positive effect on our brain during meditation and sleep, so don't forget to subscribe. I don't have any ads in this video, so nothing will interfere with your deep dive into the halls of your mind. Today we'll talk about something very interesting and significant for our galaxy. I've prepared this video for you, so you can thank me with a like. Something unexpected is taking place about 400 million kilometers from Earth. On November 16th and 17, 2025, 3 independent observing teams captured images of the interstellar comet 3I Atlas that challenge basic physical expectations. Christian Nebling and Gerald Buchner collected stacked exposures from Germany, while Michael Jaeger, Gerald Rehmann, and Rolando Ligastri worked from Austria and Italy. Their results were consistent. The comet emits narrow, sharply defined jets extending more than 1 million kilometers into space. The jets remain straight, stable, and perfectly aligned, showing no indication that the nucleus beneath them is rotating. The rotation of 3I Atlas is well established. The object completes a full spin every 16.16 hours. For any rotating body releasing gas, the expected outcome is straightforward. As the source turns, the emitted material traces out curved paths or broad fans. This behavior is evident in countless observations of cometary jets throughout the solar system. Sublimating volatiles form spirals or diffuse plumes because the surface continues to rotate during emission. This principle is simple, intuitive, and consistent with laboratory physics and spacecraft measurements. However, the jets of 3I Atlas do not follow this rule. Instead of forming arcs, they remain straight over their entire length. Instead of showing the smearing expected from dozens of rotations during the gas's travel time, they remain fixed in orientation relative to the surrounding space. If a vent on the surface is spinning with the nucleus, it should point in different directions over time, producing a spiral with each rotation. Yet the observations show narrow structures aligned with constant directions, as if disconnected from the motion of the surface. To understand the scale of the discrepancy, consider the velocities involved. Typical cometary volatiles expand at approximately 400 mph. For material to travel the observed million-kilometer distance at this speed, it would require about 2.5 million seconds, or roughly 29 days. During this period, the nucleus completes around 43 full rotations. A vent releasing gas throughout this interval should produce a feature wrapped dozens of times around the nucleus's rotation axis. Instead, we see a single, coherent, linear jet. Even if the gas were moving faster twice the typical speed, at 800 ms, the travel time would still allow around 14 to 15 rotations. To reduce the rotation count to something negligible, the velocity would need to reach tens of thousands of meters per second. At those speeds, the mechanism would no longer resemble natural sublimation. It would imply energetic processes more consistent with propulsion or explosive events than with cometary activity. For this reason, the phenomenon has been identified as the 12th major anomaly associated with 3I Atlas. Previous anomalies included non-gravitational acceleration inconsistent with standard models, an unusual brightness curve, unexpected chemical composition dominated by carbon dioxide, and unprecedented polarization patterns. Each of these traits already set the object apart from typical comets. The discovery of jets that remain unblurred despite rotation adds a new and especially difficult challenge for natural explanations. A natural hypothesis must therefore account for how the jets retain fixed orientations over long distances despite the rotation of their source. One proposal considers the geometry of the nucleus. If volatile ices are located inside shadowed craters or specific topographic depressions, they may sublimate only when illuminated from certain angles. This could produce intermittent puffs of gas once per rotation. Over many rotations, these puffs could align roughly along a similar direction, potentially creating an elongated feature. Such a mechanism is not purely speculative. Observations from the Rosetta mission to Comet 67P Churyumov-Gerasimenko demonstrated that terrain plays an essential role in controlling outgassing. Jets turned on and off as sunlight reached and left particular regions. Under specific conditions, a rotating nucleus can develop repeatable emission geometry. However, this model requires that the emission be aligned with the Sun's illumination geometry. It explains only sunward jets. Several of the November 8th images show jets extending in directions that do not correspond to sunlit areas, including anti-solar orientations where direct sunlight cannot trigger sublimation. The terrain-controlled model can be extended by suggesting reflected light, thermal lag, or internal heat retention. Yet each extension adds additional assumptions, reducing overall plausibility. Reflected light is typically too weak to drive strong sublimation, and thermal lag rarely sustains outgassing over timescales comparable to multiple rotations. A further difficulty arises when considering the expected structure of the jet. If the source emits one pulse per rotation, the resulting jet should contain a sequence of discrete clumps separated by roughly 23,000 kilometers under typical gas speeds. Over 1 million kilometers, about 43 such clumps would be expected. High-resolution imaging should reveal this structure if it exists. Current images, however, show jets that appear smooth and continuous. This does not rule out the terrain-controlled model, but suggests that additional data are required to evaluate it properly. Without detailed surface maps, thermal models, or high signal-to-noise resolved imaging, any terrain-based explanation remains speculative. The scenario requires a combination of precise geometry, specific ice distribution, and persistent illumination conditions. It is possible, but increasingly constrained. The persistence of these straight jets, unaffected by the known rotation of the nucleus, poses a significant challenge. It suggests that either our understanding of cometary outgassing is incomplete, or that 3I Atlas differs fundamentally from typical comets, whether through unusual natural conditions or through mechanisms not associated with natural bodies. Let's examine the quantitative side of the problem, because the numbers clarify why the observed jets of 3I Atlas cannot be explained by standard cometary behavior. When volatile ices such as carbon dioxide or water sublimate directly into gas, the expanding molecules reach characteristic velocities determined by their thermal energy. For typical cometary materials, this expansion speed is approximately 400 ms. This value has been measured repeatedly across multiple missions and laboratory studies and represents a reliable baseline. Now consider the jets observed on 17th of November 2025. They extend roughly 1 million kilometers from the nucleus. With a gas velocity of 400 mebarats, the time required for a molecule to travel that distance is about 2.5 million seconds, close to 29 days. During this interval, 3I Atlas completes around 43 full rotations, given its established rotation period of 16.16 hours. Any event active during this time would sweep through every possible azimuthal direction, and the emitted material would trace out a spiral or a broad rotating structure. Instead, the jets remain aligned along fixed directions. Even modifying the input parameters does not resolve the discrepancy. If we assume the gas moves at 800 meches, the rotation count would still exceed 14 full turns. Only velocities in the tens of thousands of meters per second range could reduce the rotation count enough for the jets to appear straight. But such velocities are inconsistent with thermal sublimation. They would require energy sources far more powerful than sunlight heating cometary ice. This mismatch between expected and observed behavior is not a minor detail. It points to a fundamental inconsistency. The rotating nucleus should imprint rotational motion onto its outgassing, yet the jets appear immune to this rotation. Given this situation, researchers have been revisiting the earlier anomalies associated with 3I Atlas. Since its discovery, the object has exhibited multiple deviations from expected cometary properties. The first anomaly involved non-gravitational acceleration. Typically, comets accelerate slightly due to outgassing, which acts like mild thrust. But the magnitude and direction of the acceleration detected for 3I Atlas did not match the amount of observed activity. They suggested stronger or differently oriented forces than sublimation could provide. Brightness variations form the next set of anomalies. Light curves normally reflect rotational modulation, surface reflectivity, and geometry. The pattern observed for this object deviated from standard models, implying unusual shape or albedo distributions. Spectroscopic data then revealed an unusually high carbon dioxide to water ratio in the coma. Most comets emit water as the dominant volatile. In contrast, 3I Atlas appears dominated by carbon dioxide, suggesting it formed under conditions significantly colder or otherwise different from typical comet-forming regions in known planetary systems. Polarimetric measurements added more complexity. Observations indicated that the scattered light from the coma displayed an extreme negative polarization branch, unlike any previously recorded for comets. This implies that the dust around 3I Atlas has optical properties outside the established range for natural cometary grains. By the time the linear jets were observed on 17th November, these earlier anomalies had already raised substantial questions. The jets strengthened the argument that normal cometary physics alone might not fully explain the object's behavior. Despite this, natural interpretations continue to be examined carefully. One prominent hypothesis focuses on crater geometry and shadowed ice deposits. According to this model, the nucleus might contain depressions or craters that trap ices shielded from sunlight. These regions would sublimate only when illuminated at specific rotation phases. Under such circumstances, outgassing could appear intermittent, producing discrete pulses aligned with a consistent direction. This mechanism could, in principle, create a sequence of gas clumps arranged along a roughly straight path, especially if the illumination geometry repeats each rotation. If these pulses occur every 16 hours, and the gas travels outward at typical velocities, their spacing would be predictable. Over 1 million kilometers, the clumps should form a chain of approximately 43 segments. When images with long exposure times are stacked, these clumps might blend into a continuous feature. This explanation relies on mechanisms observed on other comets. The Rosetta mission, for instance, demonstrated that topography can control outgassing on Comet 67P, producing periodic activity linked tightly to illumination. It therefore represents a physically grounded hypothesis. However, it faces significant challenges. The jets seen on 17th November include features directed away from the sun directions where sunlight cannot trigger sublimation. Models invoking reflected light or thermal lag attempt to accommodate this, but reflected light is typically too weak, and thermal lag rarely sustains activity over many hours, let alone the extended intervals needed to create features of this length. Additionally, the model requires fine-tuned geometry. The crater walls must have specific slopes, ice deposits must be precisely positioned, and the rotational axis must align favorably. The likelihood that multiple jets emerge from multiple craters with such precise configurations decreases rapidly as the number of required coincidences increases. Another point concerns stability. Sublimation reshapes surface geometry over time. A shadowed region producing a jet today may not have the same geometry weeks later. The probability that we happen to observe the object at the exact moment when such configurations align becomes increasingly small. For these reasons, the crater-based model remains viable but unconfirmed. It offers a natural mechanism consistent with known physics, but requires several assumptions without observational support. Until higher resolution data becomes available, the explanation cannot be validated or rejected definitively. The persistence of jets that remain straight and aligned over such distances despite the nucleus rotating beneath them continues to be a key unresolved problem. Whether the explanation ultimately proves natural or requires a fundamentally different mechanism remains an open question. To be fair, before we jump to anything extraordinary, we need to walk through the most grounded explanation astronomers first reached for: fragmentation. On paper, it makes sense. Comets break apart all the time. They get stressed, heated, pulled by tidal forces, blasted by uneven outgassing. They crack, split, and shed pieces like cosmic gravel kicked into space. Famous examples prove the point. Comet 73P Schwarzmann-Wachmann 3 didn't just fracture once, it shattered into dozens of pieces, each fragment developing its own tiny coma and tail. Shoemaker-Levy 9 ripped itself into a pearl string chain before plunging into Jupiter's atmosphere. Fragmentation is normal behavior for a body under strain, and 3I Atlas has certainly endured more than enough stress to justify similar behavior. It plunged inward toward the sun, endured rising temperatures and ever stronger radiation pressure, then swung back into the outer solar system. A fragile, icy body would have every reason to crack apart under those conditions. But here's where this explanation starts collapsing under its own weight. Recent observations taken after 17 November 2025, including data from the Nordic Optical Telescope and several independent imaging teams, show the nucleus of 3I Atlas appears intact. Not partially disrupted, not a loose cloud of debris, not a stretched out rubble pile, but a single compact coherent condensation. If fragmentation had occurred on the scale required to create the jets we're observing, we should see something unmistakable by now: multiple bright cores, diverging components, or diffuse spreading consistent with multiple chunks drifting apart. Instead, we see none of that. The central condensation is sharp, unified, and unmistakably single. This alone doesn't kill the fragmentation idea, but it wounds it badly. There's another issue mass. To produce jets that extend over 1 million kilometers and remain bright enough to detect from Earth, you'd need enormous ongoing mass loss. Several independent analysts, including amateur photometry groups and researchers modeling surface brightness, estimated the required dust output. Their conclusion: if these jets are actually fragment trails, the nucleus would have to be hemorrhaging material at a rate so extreme that the entire comet should have visibly shrunk by now. It hasn't. The object still looks compact and consistent with a single nucleus. There's no obvious erosion, no thinning core, no evidence of catastrophic shedding. The math simply doesn't add up. Then comes the problem of timing. Fragments breaking off at different rotation phases should head in different directions. A spinning nucleus ejects material radially, and as it rotates, each departure direction changes. If fragmentation were responsible for the multiple straight jets we observe, the fragments would need to be ejected at extremely specific rotational phases over and over, repeatedly, with almost uncanny precision to maintain the same alignment. Before considering less conventional explanations, it is important to examine the most grounded possibility. Many comets undergo structural failure as they travel through the inner regions of the solar system. Heat, radiation pressure, rotational stress, and uneven outgassing can all cause fractures or complete breakup. This process is well documented. Some objects split into multiple components. Others shed small fragments that drift away as faint dust trails. At first glance, this seems like a reasonable way to interpret the long straight features observed on 17th of November 2025. If pieces detached repeatedly from the nucleus, they could form elongated streaks extending outward from the main body. Even a modest series of breakups could produce visible structures on this scale. However, the observations do not match this scenario. Images obtained after 17 November show a nucleus that remains compact and concentrated. There are no signs of separate bright cores or diverging components. The central condensation appears unified, without indications of major disruption. If fragmentation had taken place with enough intensity to create million-kilometer structures, the nucleus would not look this intact. There is also the question of mass. To maintain such long, sharply defined streaks, enormous amounts of material would need to be released over time. Independent analyses of the dust brightness suggest that if these features were formed by fragments, the rate of mass loss would be extreme. A nucleus losing material at that level should visibly shrink, but the object shows no signs of major erosion. Timing introduces another inconsistency. A rotating body releases fragments in different directions as the surface turns. Successive pieces would naturally spread out in a range of orientations. Instead, the features associated with 3I Atlas all share a single stable direction. For fragmentation to produce this alignment, The releases would either have to occur at precisely the same rotational phase every time, or originate from a structure aligned exactly along the rotation axis. Both possibilities are physically narrow and unlikely. There is also the matter of shape. Dust trains formed by fragments usually broaden as they move outward. Differences in velocity, radiation pressure, and gravitational influences cause the material to spread, curve, or disperse. The features from 3I Atlas do not behave this way. They remain narrow and remarkably straight over their entire length. Taken together, these points leave the fragmentation model in a difficult position. It can explain occasional dust streaks or isolated events, but it does not naturally produce multiple long, straight structures that remain perfectly aligned despite the nucleus rotating beneath them. The situation becomes clearer when the inconsistencies are placed side by side. Fragmentation is common, yet no fragments are visible. A high mass loss rate is required, yet the nucleus has not diminished. The rotation should create diverging paths, yet the features line up along a single axis. Natural spreading should produce broadening, yet the features stay narrow. Each point on its own is manageable. Together they form a pattern that is hard to reconcile with ordinary breakup behavior. This does not mean the idea should be dismissed entirely. It remains possible that small-scale surface failure or minor shedding contributes to the overall appearance of the coma. But as a full explanation for the straight, long-distance structures, fragmentation does not resolve the central contradictions. At this stage, the natural models begin to show limits. Standard comet activity, regardless of how it is arranged, struggles to account for all observed characteristics at once. This leads to a broader question. If the familiar mechanisms do not fully explain the behavior of 3I Atlas, then what other physical processes could create features that remain aligned over vast distances without showing the imprint of rotation? The search for an answer continues in the next part, where the focus shifts from structural failure to the behavior of gas and dust under non-standard conditions. If fragmentation cannot fully account for the long, stable structures, the next logical step is to examine whether unusual forms of gas release might offer a better explanation. Cometary outgassing normally produces diffuse fans or curved plumes because the jets follow the rotation of the nucleus. However, there are scenarios where gas can behave in ways that differ from the common patterns. Exploring these possibilities helps clarify whether any known physical process could maintain straight, rotation-independent features over such distances. One of the first ideas to consider is highly collimated outflow. In some cases, narrow vents or deep conduits beneath the surface can channel gas into tight streams. If the geometry is right, this can create jets that appear sharper and more focused than typical comet activity. Observations from several missions have shown that terrain can guide or constrain the flow of volatiles in ways that produce surprisingly narrow plumes. This concept becomes more attractive when combined with specific thermal conditions. If an internal region warms at a constant rate, it may sustain continuous sublimation even when sunlight is not directly striking the surface. Under such circumstances, a vent might remain active for an extended period, regardless of rotation. A stable internal heat source could, in principle, keep the jet pointed in the same direction long enough for it to form a long linear structure. The difficulty lies in maintaining that direction while the nucleus turns. For a vent to preserve its orientation, it would need to be aligned almost exactly along the rotation axis. Only then would the jet remain pointed outward without sweeping across the surrounding space. This alignment is possible, but rare, and it raises additional questions about the internal structure. A vent position so precisely suggests either geological coincidence or a very specific distribution of subsurface volatiles. Even if we grant that such a configuration exists, it does not fully match the observations. The linear features extend far beyond the distance where ordinary sublimation can maintain coherence. Over hundreds of thousands of kilometers, even a highly collimated jet should gradually broaden due to particle dispersion, solar radiation pressure, and interactions with the surrounding plasma environment. Yet the features from 3I Atlas remain sharp and consistent along their length. Another angle is to consider whether the jets might be composed of particles much larger than typical cometary dust grains. Larger particles experience less divergence and are less sensitive to radiation pressure. A flow dominated by heavier material could retain a straighter profile over long distances. However, this creates a new conflict. Larger particles are less reflective, which would reduce the brightness of the streaks. For the features to remain visible from Earth, a significant portion of the material must still be fine dust or gas, which would naturally disperse. There is also the question of stability. A vent aligned with the rotation axis would still experience varying illumination over each rotation. For the activity to remain stable across many cycles, the internal heat source would need to dominate over direct sunlight. Yet comets typically lack such strong internal reservoirs. Their interiors are cold and porous, with low thermal conductivity. Heat does not easily accumulate or persist. Attempts to reconcile these issues often involve adding more assumptions. One suggestion is that the nucleus might have pockets of highly volatile ices buried deep enough to release gas through narrow pathways insulated from external temperature changes. Another is that thermal fracturing could expose fresh material periodically, maintaining a steady outflow. While possible, these scenarios require a combination of conditions that grows increasingly specific. When the model becomes too dependent on precise alignments and finely balanced parameters, it begins to lose explanatory power. A process that can occur only under rare circumstances is less likely to be the correct interpretation, especially when simpler alternatives fail as well. A more unconventional idea considers whether the gas might be following magnetic field lines. Charged particles can travel along magnetic structures with minimal dispersion. If the surrounding environment contains an organized magnetic field, the dust and ionized gas could be guided along a straight path. Observations from some comets have shown that plasma interactions can create linear features. However, these typically appear much closer to the nucleus and do not maintain coherence over such extreme distances. Additionally, for magnetic guidance to shape million-kilometer structures, an unusually strong and stable field would be required. The solar wind does contain magnetic components, but they fluctuate and shift frequently. Maintaining a fixed orientation relative to the rotation of the nucleus would require a configuration not normally found in the local plasma environment. As each natural scenario is examined, the same pattern emerges. Individual pieces of the explanation may work in isolation, but they fail when combined. A stable jet requires a fixed orientation. A fixed orientation requires specific geometry. Coherence over long distances requires minimal dispersion. Brightness requires a mix of particle sizes. Rotation should disrupt the alignment. Sublimation cannot easily maintain the necessary stability. Magnetic fields are not strong or consistent enough. Each constraint alone is manageable. Together, they form a puzzle that none of the standard mechanisms resolve cleanly. This does not immediately imply an extraordinary cause. It simply highlights that the behavior of 3I Atlas sits at the edge of what our current understanding can comfortably explain. When familiar explanations begin to falter, the next step is to examine whether combinations of processes might produce emergent effects not obvious from individual components. That exploration begins in the following section, where multiple threads of evidence are brought together to search for a cohesive physical picture. When separate explanations fail, the next step is to consider whether several natural processes could act together in a way that produces effects none of them could create alone. Sometimes a phenomenon that appears unusual is simply the result of overlapping influences that reinforce one another. With 3I Atlas, it is reasonable to ask whether a combination of geometry, thermal behavior, dust dynamics, and plasma interactions might account for the long, straight structures observed on 17th November 2025. The process begins with rotation. A nucleus that spins at a steady rate imposes a repeating cycle of illumination on its surface. If certain regions contain volatile materials that respond sharply to sunlight, they could produce bursts of activity at consistent rotational phases. These repeated emissions might align roughly in a single direction when stacked over many cycles. On their own, such pulses would produce a pattern of discrete clumps, not a continuous line. But if several other factors are present at the same time, the structure could appear more uniform. Thermal lag is one possible factor. As sunlight warms the surface, deeper layers may retain heat and release gas, even after the illuminated region rotates out of view. If the internal structure of the nucleus focuses this delayed sublimation through narrow openings, the resulting flow could appear continuous. Combined with rotation, this might create a jet that remains active longer than the exposure of any particular surface patch. Dust characteristics may also contribute. If the material contains an unusually high proportion of particles in a narrow size range, their motion could be less chaotic than that of typical cometary dust. Uniform particle size leads to more predictable expansion behavior and reduces the spread caused by radiation pressure. A jet dominated by such material would naturally maintain a tighter shape. The environment around the comet introduces additional influences. Variations in the solar wind can compress or guide ionized material into narrow channels. If a jet from the nucleus encounters a stable region of the local plasma environment, the interaction might confine the flow, helping it retain a straight profile. This effect would be modest, but when combined with thermal behavior and vent geometry, it could strengthen the overall alignment. Even these overlapping factors are not enough by themselves. The real difficulty is maintaining a single, consistent direction while the nucleus rotates. For such alignment to persist, the outflow must either originate close to the rotation axis or be guided strongly enough by external forces to override the rotation. The second possibility is limited because external forces at the comet's distance from the Sun are weak and fluctuate over time. That makes the first possibility more relevant. A vent located near the rotation axis can, under certain conditions, maintain an almost fixed orientation even as the nucleus turns beneath it. This arrangement is unusual but not impossible. Some comets have shown activity confined to localized regions near their poles. If 3I Atlas has a similar configuration, the jet could remain directed outward without sweeping across the sky. However, even this geometry has limitations. The activity must be strong enough to sustain a 1,000,000-kilometer-long structure, and the vent must remain stable through many rotation cycles. When we combine rotation axis alignment, thermal lag, particle uniformity, terrain-guided flow, and modest plasma shaping, we approach a model that can reproduce some aspects of the observed structures, but each component must be tuned with precision. A small change in particle size distribution, thermal behavior, or vent position would produce features far more diffuse or curved than what the observations show. This is the core challenge. While a multi-process explanation is physically plausible, it lacks robustness. The model works only within a narrow range of parameters, and even small deviations cause it to fall apart. Natural explanations that require this level of fine balance are rarely the best candidates, because nature tends to produce broad, messy patterns rather than consistently perfect ones. Despite this, the combined model remains the most complete natural explanation available. It accounts for the stability of the jets, their narrow shape, and their persistence over long distances. It also avoids invoking any processes beyond what we know comets can exhibit, though it pushes each of them toward the limits of what is typical. Yet one central issue remains unresolved. Even with all these factors acting at once, the model still struggles to explain how the jets maintain their straight form over 1,000,000 kilometers. Dispersion, turbulence, and interaction with the surrounding environment should gradually degrade the structure. The fact that the features remain coherent for such distances suggests either that the combined processes reinforce one another far more effectively than expected, or that an additional factor has not yet been identified. As the evidence accumulates, the phenomenon becomes more difficult to interpret through familiar comet physics alone. The observations do not break the rules of physics, but they press against the edges of what known processes can comfortably produce. When a system sits at the boundary between familiar behavior and unexplained detail, it often becomes the starting point for a deeper investigation. The next step is to examine the data collected after 17 November in greater detail, looking for clues that may narrow the range of possible interpretations. As more observations came in after 17th November 2025, the overall picture grew clearer, but not necessarily easier to interpret. The additional data confirmed the earlier structures rather than replacing them with more conventional patterns. In some cases, new images extended the visible length of the linear features, pushing them beyond the already remarkable distances previously measured. In others, the structures appeared even sharper than before, suggesting that whatever mechanism produced them was not weakening with time. One of the most important developments was the improvement in signal-to-noise ratios as multiple observers coordinated their efforts. Stacked exposures reduced background interference and increased the clarity of the faintest parts of the jets. The structures did not fade into diffuse clouds farther from the nucleus. Instead, they retained their straight, narrow profile for as long as the images captured them. This reinforced the idea that dispersion was far weaker than expected. The consistency of these features across different instruments added credibility. When separate observers in different countries detect the same structures using unrelated equipment, the likelihood of an instrumental artifact becomes very small. This cross-confirmation helped eliminate one class of potential explanations, narrowing the focus to physical rather than observational causes. Another useful result came from comparing sequences of images taken at different times. If the structures were tied directly to rotation, their orientation should shift predictably as the nucleus turned. But the direction of the jets relative to the background stars remained almost unchanged from one observation period to the next. This stability implied that either the jets were aligned with the rotation axis itself, or that external influences were dominating the direction, which seemed unlikely given the variability of the surrounding environment. At the same time, subtle variations in brightness along the jets hinted at complex internal structure. Some regions appeared slightly denser, while others seemed more faint. These variations did not form a periodic pattern, which would have been expected if the emission were purely rotational. Instead, they appeared irregular but coherent, suggesting that the underlying mechanism might vary but still operate in a consistently aligned manner. Spectroscopic readings provided another layer of information. The material within the jets appeared dominated by fine dust and ionized gas, with a composition similar to the comet's general coma. There were no signatures indicating unusual elements or exotic compounds. This was an important point. The jets did not appear to be made of unfamiliar material. Their mystery lay not in what they were composed of, but in the way that material behaved on such large scales. The environment around 3I Atlas also played a role in shaping the next stage of interpretation. The comet was moving through a region of the solar wind that, while variable, showed some temporary stability in magnetic and plasma conditions. This raised the possibility that the jets might be interacting with a localized structure in the solar wind, helping them maintain their alignment. However, even in a stable environment, maintaining a straight path over such extreme distances remained difficult to justify through plasma interactions alone. One interesting development came from modeling the motion of dust particles under combined forces of solar radiation pressure and the solar wind. Simulations indicated that if the initial outflow velocity was unusually uniform, and the particles were confined to a narrow size range, their trajectories could remain aligned longer than typical cometary jets. But these conditions would need to be remarkably consistent over time. Any deviation in particle size distribution or outflow velocity would quickly lead to spreading. These models also showed that even under ideal circumstances, maintaining a straight structure beyond several 100,000 kilometers was challenging. Extending this coherence to 1,000,000 kilometers or more required parameters that left little margin for natural variability. The slightest shift in the source region, illumination angle, or external plasma conditions would distort the feature. Yet the images showed no such distortions. Taken together, the new observations reinforced the central puzzle rather than resolving it. The structures remained consistent, stable, and significantly straighter than any natural jet model predicted. They did not resemble debris trails, magnetic filaments, or typical gas plumes. They appeared as something that held its form through conditions that normally degrade or scatter cometary emissions. As the data accumulated, researchers began to categorize the phenomenon not as an isolated anomaly, but as part of a broader pattern of unusual behavior displayed by 3I Atlas. The linear jets were one piece of a larger collection of characteristics that did not fit easily within the established framework of comet physics. The unusual brightness curve, the high carbon dioxide content, the polarization features, the non-gravitational acceleration, and now the long straight jets all pointed in the same direction. None of them contradicted known physics outright, but together they formed a picture that did not align with typical comet behavior. The emerging question shifted from whether each individual anomaly could be explained to whether a single underlying cause might connect all of them. When multiple independent deviations appear within one object, the explanation often lies not in a series of unrelated coincidences, but in a single factor that influences all the observed properties. Identifying that factor became the next goal. The following section examines whether the combined anomalies suggest a structural or compositional origin, or whether the underlying cause might lie in the dynamics of the object's motion through the solar system. As the anomalies surrounding 3I Atlas accumulated, the focus naturally shifted toward understanding whether they stem from the object's internal structure or from the way it moves through space. Comets often behave unpredictably, but when several unusual traits appear together, it becomes more productive to look for a unifying explanation rather than addressing each feature separately. A single underlying factor can often clarify a group of observations that seem unrelated at first. The first possibility to consider is that the nucleus has an unusual internal composition or architecture. If the material inside the object is arranged in a layered or uneven manner, it might influence outgassing in unexpected ways. Cavities, porous channels, or internal fractures could guide gas into narrow, stable pathways. In this case, the long linear structures might be a surface-level expression of a deeper internal system. The gas would not simply escape from exposed regions, but would follow existing conduits created during the object's formation. Such an internal system could also explain the unusually high proportion of carbon dioxide detected earlier. If much of the water ice was buried deeply, it would sublimate less efficiently, allowing carbon dioxide to dominate the coma. This compositional imbalance might indicate that the object originated in a region much colder than typical comet-forming zones. If the interior formed under extreme temperatures, the resulting structure could preserve volatiles in configurations rarely found in comets from the solar system. Another line of inquiry considers the object's shape. If the nucleus is elongated or irregular, with one end significantly different from the other, the distribution of sunlight and thermal energy across its surface could become very uneven. This uneven distribution might create stable, long-lasting outflow directions that do not change much as the nucleus rotates. A jet emerging from a region near a pole of an elongated body would not sweep out the wide arc expected from equatorial sources. This would make the jet appear steadier and more aligned than normal, provided the rotation axis and the geometry of the nucleus were arranged in just the right way. Studying the motion of 3I Atlas adds another dimension to this interpretation. Its non-gravitational acceleration was one of the first anomalies noted. The direction and magnitude of this acceleration did not perfectly match what would be expected from symmetric gas release. If the jets visible on 17th of November represent the main outgassing channels, they could influence the comet's trajectory. A stable jet pointed in one direction would act like a constant gentle thrust. Over time, even a small force could shift the orbit enough to create measurable deviations. This brings the discussion to an important idea. The stability of the linear jets and the persistent non-gravitational acceleration might not be separate mysteries. They may be different expressions of the same underlying process. A well-aligned jet would naturally produce both a visible structure and a consistent push on the nucleus. If the internal configuration of the comet channeled gas through a fixed pathway, this single mechanism could explain both phenomena at once. Even so, there are limits. For the jet to maintain alignment while the nucleus rotates, the source must be positioned close to the rotation axis. If the source is even slightly displaced, the rotation should cause the jet to sweep around and form a spiral. The stability of the jets therefore implies an unusually precise geometry. While possible, it requires a level of structural alignment that is statistically uncommon. Some researchers also considered whether the nucleus might be experiencing a form of rotational damping. If internal mass redistribution reduces the wobble or tilt of the rotation axis, the jet could become more stable. But this requires a delicate balance between the internal forces and the outflow, and observational data does not yet show any evidence of changes in rotational motion. For now, the rotation seems steady. The external environment remains another point of interest. Although plasma interactions alone cannot create million-kilometer structures, they can influence the behavior of ionized material near the nucleus. If the comet is passing through a region of the solar wind with an unusually consistent flow pattern, the local conditions might help maintain the alignment of the jet. This effect would be subtle, but in combination with internal geometry and thermal behavior, it might reinforce the direction of the outflow. Still, the observations demand caution. It is easy to construct models that rely on a series of precise conditions, each one just barely within the realm of possibility. The challenge is to produce an explanation that remains stable even when the conditions vary slightly. A model that works only under narrow circumstances is less convincing than one that remains valid across a broader range of parameters. At this stage, the evidence suggests that natural explanations exist, but require an unusually specific combination of internal structure, geometry, particle behavior, and environmental conditions. None of these factors violate known physics, but assembling them into a coherent model demands a degree of precision that makes the object stand out among known comets. The next step is to consider whether this level of precision emerges from a natural origin or suggests a formation history that differs from typical cometary bodies. In exploring this question, the analysis turns toward the deeper issue of where 3I Atlas came from and whether its journey through interstellar space might have shaped its internal structure in ways unfamiliar to objects formed within our own system. To understand whether the characteristics of 3I Atlas could originate from its formation history, it helps to consider the environment in which the object may have developed long before it entered our solar system. Interstellar space contains a wide range of conditions, many of which differ significantly from the regions where comets in our system typically form. These differences can influence composition, internal structure, and even long-term evolution in ways that become visible only when the object becomes active near a star. Most comets in the solar system formed within regions containing abundant water ice. Temperatures in those areas were low enough to preserve volatile materials, but not so extreme as to eliminate water as the dominant component. However, the unusually high carbon dioxide content of 3I Atlas suggests formation under much colder conditions. In such environments, water remains frozen at levels that prevent sublimation even under moderate heating, while carbon dioxide becomes comparatively more mobile. This could lead to a nucleus structured in layers, with deep reservoirs of trapped volatiles that behave differently when heated. Extended exposure to interstellar radiation may also have altered the object. Over millions of years, cosmic rays can penetrate the surface and reorganize the chemistry of the upper layers. This can create complex organic crusts, dense outer shells, or hardened regions that restrict gas flow to narrow channels. If 3I Atlas spent a long time in interstellar space, the outer surface may have evolved into a rigid layer while the interior remained volatile rich. A configuration like this would naturally create focused outflow when heated, because the gas would escape only through limited weak points. Another factor is the mechanical stress induced by repeated temperature fluctuations during long journeys near different stars. If the object passed near multiple stellar systems before arriving here, each encounter could have caused cycles of heating and cooling. Over long timescales, such cycles may produce deep fractures, internal caverns, or aligned voids that guide volatile release in specific directions. This possibility remains speculative, but it fits within the range of what is known about long-term material fatigue in icy bodies. Its trajectory into the solar system adds another clue. The path of 3I Atlas does not match the pattern expected from an object gently drifting in from interstellar space. Instead, its motion suggests it may have passed relatively close to other gravitational bodies before arriving. These encounters could have modified its rotation axis or altered its internal stress distribution. If the rotation axis shifted recently in astronomical terms, internal structures that once released gas in multiple directions may have become aligned in a way that now points outflow along a stable orientation. Understanding how these factors interact becomes essential when considering the linear jets observed on the 17th November. A narrow vent aligned with the rotation axis can remain pointed in a consistent direction even as the nucleus spins. If that vent formed through processes that unfolded over millions of years in interstellar space, it would explain the precision of the alignment without requiring recent structural changes. The combination of an interstellar formation environment and subsequent evolutionary processes could therefore set the stage for the unusual behavior seen today. This leads to a broader question. If the internal configuration of 3I Atlas is responsible for the anomalies, then the object might represent a category of bodies formed under conditions not previously sampled. Most comets observed so far formed in a small range of environments within the solar system. An interstellar object, by contrast, may reflect the diversity of conditions present across the galaxy. The sharp jets, unusual composition, and non-gravitational acceleration may all be signatures of a formation history different from anything encountered locally. Even so, this viewpoint must be approached carefully. A unique formation environment alone does not guarantee the level of precision required for the observed features. The narrow alignment, extraordinary straightness, and persistence of the jets still require an internal configuration that is unusually stable. A body shaped by random interstellar processes would likely develop complex and irregular structures, not the finely tuned pathways implied by the data. This is where the analysis becomes more nuanced. The interior of 3I Atlas may not be random. If its formation environment favored specific crystallization patterns, or if the object condensed from material influenced by directional flows, shocks, or magnetic fields, the resulting structure might possess natural alignment. Some astrophysical environments produce dust grains and icy aggregates with preferred orientations. If the nucleus inherited those patterns, it could retain a built-in directionality long after leaving its birthplace. In this sense, the object's behavior may be the combined result of both formation and long-term evolution. A naturally aligned internal structure, hardened over time by interstellar radiation, could channel gas tightly enough to withstand external disturbances. This would allow the jets to maintain their direction even as the nucleus rotates, and could produce the straight, stable structures captured in the observations. The challenge moving forward is determining how much of the observed behavior can be attributed to the internal makeup of the object and how much to external conditions. Only by understanding the interplay between these factors can we assess whether the anomalies represent extreme but natural behavior or point towards something that falls outside the expectations for cometary physics. With this in mind, the next part explores what the combined anomalies imply about the long-term stability, energy balance, and internal mechanics of 3I Atlas, and whether these point toward a coherent natural explanation. As attention shifted toward the long-term stability and internal mechanics of 3I Atlas, the goal was not only to describe what the object is doing now, but to understand how these behaviors can persist over time. A system that maintains precise alignment across multiple observations must have an internal balance that resists disturbance. This introduces questions about the distribution of mass inside the nucleus, the strength of structural bonds, and the efficiency with which energy is absorbed and released. One of the first considerations is how the object manages the energy it receives. Comets typically absorb sunlight, warm unevenly, and release gas in pulses that reflect those fluctuations. The irregularity of this process creates the variability seen in most cometary jets. In the case of 3I Atlas, however, the emission appears steadier and more uniform than expected. This suggests that the nucleus may be distributing thermal energy more evenly than a typical comet. If the interior is composed of materials with higher thermal conductivity or contains pathways that move heat deeper into the body, the response to sunlight could become smoother and more controlled. A stable release of energy would not fully explain the alignment of the jets, but it would help sustain them once they form. If the internal structure retains heat and channels it through consistent points, the outflow would continue long after surface illumination changes. This behavior would contribute to the persistent linear features seen in the images taken on and after 17th of November. The next aspect involves the internal distribution of mass. A nucleus with uniform density tends to rotate predictably, but one with pockets of different materials or large voids can wobble or shift as it spins. Any such irregularity would influence the direction of outgassing. The fact that the observed jets remain aligned suggests that the object's rotation is steady and that internal mass is arranged in a way that avoids significant wobble. This does not require a perfectly uniform interior, but it does imply that the mass distribution is stable enough to prevent changes in the orientation of the rotation axis. Another possibility is that the object contains rigid structures that support stable pathways for escaping gas. If certain areas of the nucleus are hardened by interstellar radiation or formed from materials that compact over time, they could create durable conduits. These conduits would focus outflow more effectively than the loose, porous matrices found in typical comets. Structures like this would also resist deformation as the object rotates, helping preserve the orientation of the jets. There is also the question of mechanical stress. A nucleus undergoing active sublimation experiences pressure from within as gas builds up and seeks escape routes. In most comets, this pressure eventually causes fractures that redirect outflow or create new vents. But if 3I Atlas has a reinforced surface layer or a strong internal skeleton, it could channel pressure through only a few established openings. This would reduce the chance of new vents forming and maintain the stability of the existing ones. A related consideration is rotational strain. If the nucleus spins at a moderate rate, internal stresses may remain low enough to avoid new fractures. The rotation period of 16.16 hours is slow enough to prevent significant centrifugal disruption, allowing the internal pathways to remain intact. A faster spin might disrupt this stability, while a slower spin might alter the heating pattern. The current rate appears to support the observed behavior, suggesting that the rotation period plays a role in maintaining the alignment of the jets. External influences must also be taken into account. The comet travels through an environment shaped by the solar wind, radiation pressure, and magnetic fields. While these forces fluctuate, they can create temporary regions of relative stability. If the jets interact with such a region, even weakly, the surrounding conditions could help reinforce the direction of the outflow. The effect would not be strong enough to create the structures alone, but it could enhance their coherence once formed. These combined factors paint a picture of an object whose internal and external conditions both contribute to the unusual features. Yet the most important point is the degree of precision involved. A system that produces a straight, stable jet over 1 million kilometers must maintain alignment with remarkable consistency. Any shift in internal pressure, structural weakness, rotational wobble, or environmental change would introduce curvature or dispersion. The absence of such deviations suggests a balance that is rare among cometary bodies. This leads to a broader implication. If the internal makeup of 3I Atlas is responsible for the observed features, then the object may represent a type of comet with properties not commonly found in our solar system. It might be part of a population formed under conditions that favor strong internal structuring or specific crystalline patterns. Alternatively, its stability could result from processes that occurred during its long interstellar journey, shaping it into a form that supports narrow, persistent outflow channels. Understanding which of these possibilities is more likely requires revisiting the interplay between composition, structure, and environmental history. If the features arise naturally from the object's formation and evolution, then 3I Atlas offers a rare opportunity to study a class of bodies that rarely pass near the Sun. If the features require more precise alignment than natural processes typically produce, then the object may represent an outlier whose behavior challenges current models. The next step is to examine how all known anomalies, composition, brightness, acceleration, polarization, and the linear jets can be interpreted together. Only by looking at the entire set of observations as a unified whole can we evaluate whether a natural explanation remains consistent. When all observed anomalies of 3I Atlas are considered together, a clearer pattern begins to emerge. Each individual feature can be interpreted within the boundaries of known physics, but the combination of these features occurring in a single object raises more complex questions. Understanding this requires looking not at isolated effects, but at how they interact and reinforce one another. The unusually high carbon dioxide content suggests a formation environment much colder than typical cometary regions. The extreme negative polarization indicates dust grains with uncommon optical properties. The non-gravitational acceleration signals a sustained directional force. The stable brightness curve reflects steady energy release. And the long straight jets observed on 17th of November reveal a mechanism capable of maintaining remarkable alignment over vast distances. Taken one at a time, each of these anomalies can be explained through specific natural mechanisms. But when combined, they point toward a nucleus with an internal structure and thermal behavior that differ significantly from familiar comet types. This raises the possibility that the object's unusual traits do not arise independently, but from a single underlying cause. One approach is to consider whether a rigid internal framework could unify the observations. If the nucleus contains hardened regions or crystalline structures shaped by interstellar conditions, these could influence thermal conductivity, restrict outgassing to specific pathways, and maintain stable vents close to the rotation axis. Such a framework might also contribute to the unusual polarization by producing dust with consistent particle shapes and sizes. In this scenario, the same internal features responsible for the polarimetric anomaly could also create the narrow outflow channels that maintain the jet alignment. Another possibility is that the object's composition leads to slow and uniform heating. A nucleus dominated by deep layers of carbon dioxide ice may respond more gradually to sunlight, releasing gas at a steadier rate than a water-rich comet. This stable energy release would support a constant outflow from specific vents, reinforcing a narrow jet that does not fluctuate dramatically with each rotation. A steady flow would also contribute to non-gravitational acceleration by providing a persistent thrust. If these two effects, rigid internal structure and gradual thermal response, occur together, they could produce a set of behaviors that match the observations more closely than any single mechanism. A consistent internal framework would maintain the direction of the vent, while stable heating would support continuous outflow. The combination could naturally generate long, straight structures even in the presence of rotation and external environmental variability. However, this interpretation still requires a level of precision that stands out among cometary bodies. Even with a rigid internal framework, maintaining a perfect alignment over 1 million kilometers remains challenging. Natural processes tend to introduce irregularities, especially when influenced by rotating structures and variable external forces. Yet the features captured after 17 November show little evidence of such irregularities. This brings forward another idea, that the anomalies may reflect the object's evolution across interstellar space, where long-term radiation exposure, temperature cycling, and micro-impacts could gradually produce a uniquely stable configuration. If internal channels or voids developed slowly over millions of years, they might become deeply anchored within the nucleus. Once established, such channels could persist as long-term, stable pathways for gas release. An object shaped by interstellar evolution could therefore exhibit a combination of traits not found in comets formed within the solar system. This would explain why the observations seem so unusual when compared to ordinary cometary behavior. Instead of being an outlier within local comet physics, 3I Atlas might simply reflect a different category of body shaped by conditions we rarely observe directly. Even with this interpretation, questions remain. For example, the non-gravitational acceleration is unusually consistent. A stable vent aligned with the rotation axis could produce continuous thrust, but the precision and persistence of the acceleration still exceed typical expectations. Likewise, the extreme polarization suggests dust with uniform properties, which may indicate a highly controlled production mechanism. These features imply that the internal structure must be both stable and remarkably consistent. Another layer of complexity appears when the brightness curve is examined in detail. The variations do not follow the simple rotational modulation expected from an uneven surface. Instead, the curve shows smooth transitions that suggest a more controlled release of energy. This behavior reinforces the idea that the interior regulates outgassing in a uniform way, further supporting the hypothesis of a structured internal framework. When all these elements are combined, a coherent picture becomes possible. A nucleus formed in an unusually cold environment could preserve deep reservoirs of specific volatiles. Interstellar radiation could harden the outer layers, creating a robust shell with limited weak points. Internal voids and channels could align along a specific axis. When the object approaches the Sun, stable heating could activate only those channels, producing long, straight jets that maintain orientation as the body rotates. The same configuration could produce consistent non-gravitational acceleration and influence the physical properties of the dust. This model does not require any processes beyond known physics, but it does require a rare combination of factors working together. The rarity itself may be the reason why objects like 3I Atlas are not observed frequently. Interstellar space likely contains a wide variety of bodies shaped under distinct conditions, and most may never pass close enough to the Sun for their internal structures to become visible. With this combined picture in place, the next step is to examine whether the anomalies point toward natural but uncommon evolution, or whether they suggest a system shaped by influences not typically associated with cometary bodies. With a combined natural model in place, the next challenge is to evaluate whether the observed behavior of 3I Atlas can be fully explained through uncommon yet feasible cometary evolution, or whether it hints at influences that fall outside the boundaries of typical natural development. This does not imply extraordinary conclusions, but it does require examining how far known processes can be stretched before they cease to provide consistent explanations. One important step is to consider the internal environment of the nucleus as a dynamic system rather than a static structure. Over long timescales, internal cavities, fractures, and channels evolve in response to mechanical stress, volatile migration, and repeated exposure to varying temperatures. These processes can gradually refine pathways for gas release, making them narrower, more stable, or more directionally aligned. If 3I Atlas experienced extreme cycles during its interstellar journey, its internal features may have reached a level of refinement uncommon among solar system comets. For example, repeated exposure to cosmic rays can gradually compact certain materials while weakening others. This could create a contrast between rigid, load-bearing sections and softer, volatile, rich pockets. Over time, this contrast may guide the formation of long, narrow conduits capable of maintaining their shape even under thermal stress. Such conduits could channel gas in a focused manner, supporting jets with unusual stability and coherence. At the same time, the distribution of volatiles within the nucleus could influence the direction and strength of outgassing. If deep reservoirs of carbon dioxide ice are concentrated along a particular axis, the heating pattern would naturally reinforce that orientation. As sunlight warms the nucleus, the activation of these reservoirs would produce consistent thrust along the same axis. This would help explain the persistent non-gravitational acceleration measured during the object's approach. Even so, the degree of precision implied by the jets observed on 17th of November remains striking. Natural processes often introduce irregularities that accumulate over time. Fractures do not remain perfectly aligned. Pressure does not build uniformly. External forces vary, yet the jets captured in multiple observations remain consistently straight. This level of stability suggests that the internal configuration is not only anchored but deeply integrated into the physical structure of the nucleus. Another factor to evaluate is the rotational dynamics. A body with an axis-aligned vent must maintain a stable rotation for the configuration to persist. Any significant precession or wobble would cause the jet to drift. The available data shows no strong indication of rotational instability. This supports the idea that the rotation axis has remained steady, possibly for a long period. A stable axis would naturally reinforce the orientation of any pre-aligned internal conduits. The strength of the linear jets also raises questions about the efficiency of the outgassing mechanism. A 1 million-kilometer-long structure requires sustained particle flow with minimal dispersion. This implies not only a stable vent, but also consistent outflow velocity and particle size distribution over time. Inside the nucleus, this consistency could be driven by the geometry of the conduits. If the channels narrow as they approach the surface, they can act as natural regulators, smoothing out variations in pressure and preventing chaotic bursts of material. Such narrowing is physically plausible and may arise from long-term sublimation and redeposition within the channels. The external environment must still be considered, even if it plays a supporting rather than primary role. A region of relative stability within the solar wind could help maintain the linear appearance by reducing turbulence near the comet. Minor interactions between the outflow and the surrounding plasma might reinforce the direction of the jet without needing to dominate its behavior. These influences would not create the features on their own, but they could help preserve them. Once all these processes are combined, the result is a natural model that aligns with the observations. But the model remains finely tuned. It rests on specific internal configurations, stable rotation, consistent outflow, and favorable external conditions. Each element is plausible, but the overall precision is unusual. This raises the question of how likely such a configuration is to form and persist without additional shaping influences? Exploring this question requires considering the object's broader evolutionary history. If its internal structure was shaped over millions of years in interstellar space, subjected to extreme conditions, and gradually refined by long-term thermal cycles, then the precision observed today may reflect that extended evolution. The object might simply represent a rare but naturally evolved configuration. In that sense, 3I Atlas would not be extraordinary, but rather an example of a class of objects seldom seen near any star. However, if the required alignment and stability exceed what long-term natural processes typically produce, then the object may represent a more unusual case. It may belong to a narrow subset of interstellar bodies shaped by specific events or conditions. This does not imply anything beyond natural physics, but it highlights that our sample of such objects is extremely limited, making it difficult to establish how common or rare these configurations truly are. Regardless of which interpretation is correct, the significance remains the same. The combined anomalies point toward an internal structure and evolutionary history that differ fundamentally from typical solar system comets. Understanding this helps frame the next question, whether the behavior of 3I Atlas suggests a unique origin or whether it reflects broader variations in interstellar bodies that we have not yet observed. The next part examines how the object's motion, composition, and structural features may connect to potential formation environments across the galaxy, and whether these environments could naturally produce the precise characteristics seen in the observations. Understanding the origin of 3I Atlas requires looking beyond its current behavior and considering the environments in which such an object could naturally form. The precision of its internal structure, the stability of its outflow, and the unusual combination of volatiles all point toward conditions that differ from the familiar regions where solar system comets originate. To explore this possibility, it is helpful to examine a range of astrophysical environments known to produce icy bodies, and to consider how each could influence the properties observed on and after 17 November. One candidate environment is the outer regions of protoplanetary disks around young stars. These areas contain cold, dense clouds of gas and dust where ices condense onto small grains. The extreme cold could allow carbon dioxide to accumulate in deeper layers while water ice forms farther outward. If the temperature profile of the disk were sharply stratified, the resulting object might develop internal layers dominated by different volatiles. Over time, these layers could become compacted into stable configurations that influence the direction and strength of outgassing once the body becomes active near a star. Another possibility is formation inside dense molecular clouds, where temperatures can drop even lower than in typical protoplanetary disks. In such environments, particles can grow under extremely cold conditions, creating aggregates with unique crystalline structures. These structures might naturally align in preferred orientations due to the influence of local magnetic fields or directional flows within the cloud. If 3I Atlas formed in such a region, it could have inherited internal patterns that later guided outgassing along stable axes. A third scenario involves gravitational encounters early in the object's history. If the forming nucleus passed near a massive body during its development, tidal forces could impose structural stress that reorganized its interior. Such processes might generate long, narrow fracture systems that persist even after the object leaves its natal environment. If the internal fractures aligned along a particular direction, they could create the pathways responsible for the stable jets seen in recent observations. It is also worth considering the influence of shockwaves within star-forming regions. These shockwaves, produced by stellar winds or supernova remnants, can compress materials into aligned filaments. If the object condensed within one of these filaments, the resulting structure might contain elongated internal features that survived the transition from dust cloud to solid nucleus. When heated near a star, these features could act as natural conduits for gas release. Regardless of the specific environment, the key idea is that certain regions of the galaxy possess conditions capable of producing icy bodies with strong internal alignment. If 3I Atlas formed in one of these environments, its unusual characteristics may reflect not an anomaly, but an expression of physical processes that are simply uncommon in the solar system. In that sense, the object might act as a sample of distant astrophysical conditions, offering insight into how comets evolve under different initial conditions. Once formed, the object would have entered interstellar space, where it spent millions of years exposed to radiation, impacts from microscopic grains, and cycles of heating and cooling during distant stellar encounters. Over this time, any internal alignment inherited from its formation environment could become more pronounced. Radiation can harden surfaces, deepen existing channels, and erode softer materials, gradually refining the internal structure. Voids may expand or merge, and stable conduits may become more distinct. The outcome would be a nucleus with enhanced directional properties that persist through long periods of activity. The influence of interstellar evolution does not stop there. As the object travels through regions with varying densities and temperatures, its surface chemistry evolves. Layers of irradiated material can accumulate and act as insulating shells. These shells restrict gas to specific exits, channeling outflow along predetermined paths. In this way, interstellar conditions could reinforce the structural precision required to produce long, straight jets once the object is heated again. When 3I Atlas entered the solar system and became active, these internal features would be revealed. The stable vents responsible for the linear jets could reflect channels preserved for millions of years. The unusual volatile composition could reflect both its formation environment and long-term chemical processing. The non-gravitational acceleration could arise from outflow guided by those ancient aligned conduits. Viewed together, these phenomena point toward an origin far removed from the familiar processes that shape typical comets. However, questions remain about how such alignment remains preserved despite the stresses associated with activation. When exposed to sunlight, sublimation pressures can cause internal fractures that alter existing pathways. Yet in this case, the features remain stable across multiple observations. This suggests that the internal channels are not fragile, but deeply embedded within a durable framework. Such a framework could be the result of the intense compaction and crystallization that occur in extremely cold or high-pressure formation regions. Considering these possibilities refines the picture of 3I Atlas as an object shaped by conditions not sampled in the solar system. The linear jets, unusual polarization, and stable acceleration may not be isolated anomalies, but natural outcomes of its origin and long-term evolution. This interpretation places the object within a broader astrophysical context, where its properties reflect processes common in the galaxy, even if they are rare in our local neighborhood. The next step is to examine whether the object's current behavior provides additional clues about how these internal structures operate under changing conditions, and whether the ongoing observations continue to support the idea of a naturally evolved, highly aligned interstellar body. As observations continued beyond 17th of November, the behavior of 3I Atlas offered additional insight into how its internal structures respond to changing environmental conditions. Studying these changes is essential because they reveal whether the internal pathways responsible for the linear jets are stable only under specific circumstances, or whether they persist as the surrounding environment evolves. The stability of these pathways provides clues about the underlying mechanisms shaping the object. One of the most informative developments was the gradual change in solar illumination as the comet moved along its trajectory. Even small variations in the angle of sunlight can influence outgassing, especially when different parts of the surface become active or inactive with each rotation. In most comets, these changes produce noticeable differences in jet patterns. However, the linear features of 3I Atlas remained consistent even as the illumination changed. This indicates that the internal conduits dominating the outflow do not depend strongly on direct surface heating and are likely connected to deeper reservoirs less affected by surface variability. Another useful observation came from changes in the surrounding plasma environment. As the solar wind fluctuates, it can alter the morphology of coma structures. Most comets respond visibly to these shifts, with ion tails rippling or curving in response. In the case of 3I Atlas, the narrow jets remained largely unaffected, which suggests that the outflow velocity and concentration were high enough to overcome minor disturbances. This reinforces the idea that the jets are shaped primarily by the internal structure rather than external forces. At the same time, subtle variations in jet brightness revealed that the internal activity is not entirely uniform. Certain regions along the jets brightened slightly over time, while others dimmed. This behavior indicates changes in the amount of material released through the conduits. These fluctuations do not alter the direction of the jets, but they show that the internal system is dynamic. Volatile reservoirs may be gradually depleting, or pressure may vary as different pockets of material become active. Despite these internal changes, the overall alignment remained constant, suggesting that the structural framework guiding the flow is stable enough to preserve direction even as local conditions vary. Thermal modeling adds further clarity. As the nucleus absorbs sunlight, heat slowly penetrates deeper layers, activating material previously held in colder regions. Over time, this can shift the balance of outgassing within the nucleus. If the internal structure were fragile or loosely connected, these shifts would alter the orientation of the jets. But the fact that the jets retain their alignment implies that the conduits are anchored within durable, rigid regions. These regions may consist of compacted material formed under high pressure or crystalline structures that maintain their alignment even under thermal stress. The gradual decline in solar distance after the object's closest approach also provides information. As the comet moves away from the Sun, outgassing normally decreases. Yet during this period, the linear jets remained visible, though their intensity slowly diminished. This continued activity suggests that the internal pathways remain functional even under reduced heating. Such behavior is consistent with a system where deep reservoirs continue to release gas slowly after being warmed earlier. It also suggests that the conduits themselves do not collapse as pressure decreases, reinforcing the idea of a rigid internal framework. These observations support the interpretation that the internal structure of 3I Atlas is not only precise but also resilient. It retains its alignment through variations in illumination, plasma conditions, and internal pressure. This resilience implies that the conduits responsible for the jets are not transient features, but long-standing components of the nucleus, shaped over extended periods of evolution. However, this stability also raises questions. If the internal conduits are so well preserved, what processes formed them in the first place? Their durability implies strong bonds and an organized structure rather than a random network of fractures. This again points toward a formation environment where materials could crystallize or compact under conditions that produce aligned patterns. Once created, these patterns could survive interstellar travel and become active when heated near a star. Another notable aspect is the behavior of the coma surrounding the jets. The general coma remained diffuse and irregular, showing the expected variability of typical cometary activity. This contrast highlights that the linear jets arise from a highly specific mechanism rather than the global processes that shape the rest of the coma. The jets appear as distinct, well-defined features within a more chaotic environment, underscoring their unique origin within the nucleus. This duality-stable internal conduits producing precise jets within a variable outer coma suggests a multi-layered structure inside the nucleus. The outer layers may behave like those of ordinary comets, responding to sunlight with irregular sublimation, while the inner regions maintain long-term stability. This layered structure could naturally arise if the outer layers were modified by interstellar radiation or impacts, forming a hardened shell, while the deeper regions preserved ancient internal patterns. These observations strengthen the case that 3I Atlas is best understood as a product of both uncommon formation conditions and long-term evolution. Its behavior does not require physics beyond what is known, but it does reflect combinations of properties that rarely appear together. The object stands as a reminder that interstellar bodies may carry structural and compositional signatures of environments far more diverse than those present in the solar system. The next part explores how these insights reshape our understanding of interstellar objects as a whole, and what 3I Atlas may reveal about the broader population of bodies traveling between stars. As the behavior of 3I Atlas becomes clearer, its significance extends beyond the object itself. The insights gained from its observation help refine our understanding of interstellar bodies more broadly. Until recently, only a small number of such objects had been directly observed entering the solar system. With so few examples, each new case provides valuable information about the diversity of materials, structures, and evolutionary paths that can emerge in other planetary systems. The previous interstellar visitors showed that these objects do not necessarily resemble the comets and asteroids seen locally. Their trajectories, compositions, and brightness patterns revealed differences that challenged initial assumptions. 3I Atlas continues this trend, offering a deeper look into how interstellar objects may carry physical characteristics shaped by environments rarely encountered near our Sun. One major implication is the range of possible internal architectures. Typical solar system comets often display porous, loosely bound interiors that respond to heating with irregular activity. By contrast, the behavior of 3I Atlas suggests a nucleus with more organized internal pathways capable of sustaining stable outflow. This indicates that interstellar objects may originate in environments where materials form under higher pressure, lower temperature, or stronger magnetic influence than in our local system. If so, bodies formed in those regions would naturally display unique thermal and mechanical properties once activated. The persistence of the long linear jets highlights another important point. Their alignment suggests the presence of deep conduits or fracture systems that maintain their structural integrity across long periods of activity. This kind of internal stability implies that interstellar space does not simply erode or randomize internal features. Instead, it may preserve them through processes that harden surface layers and reinforce existing structures. Repeated cycles of heating and cooling, combined with exposure to cosmic radiation, could gradually strengthen the nucleus rather than weaken it. This raises the possibility that many interstellar objects may retain complex internal signatures from their origins. Each object entering the solar system could carry a record of conditions in distant star-forming regions. If enough such objects are observed, their properties may reveal a spectrum of environments across the galaxy, offering indirect insights into planetary system formation beyond the solar system. Another implication concerns the role of volatiles in interstellar evolution. The unusual carbon dioxide content of 3I Atlas suggests that volatiles can accumulate in layers or pockets with unexpected compositions. If bodies form at extremely low temperatures, they may trap materials that do not usually dominate cometary activity near the Sun. These materials can become important markers of the object's birth environment. In this case, the CO2-rich composition points toward formation in a region colder than most parts of the solar system's protoplanetary disk. The stable non-gravitational acceleration provides another clue. A consistent force acting on the nucleus implies that aligned outgassing is not accidental, but part of a long-term structural feature. If this alignment originates from conditions present during formation, it may offer evidence that some interstellar objects develop symmetry or orientation preferences within their internal structure. Over millions of years, these patterns may become reinforced by interstellar processes, allowing them to persist through the object's approach toward a star. The extreme polarization observed earlier fits into this broad pattern. The dust particles released from the jets appear to share similar shapes and sizes, which again suggests a controlled production mechanism. If the dust originates from deep, well-protected reservoirs, its properties may reflect ancient material preserved since the object formed. This makes the dust a potential indicator of physical and chemical processes that took place in distant regions of the galaxy. All these observations point toward a simple but important idea. Interstellar objects may not be outliers in their own environments. They are outliers only when viewed from the perspective of the solar system. The physical processes shaping them could be common in regions of the galaxy we have not yet studied directly. Their unusual properties therefore provide an opportunity to expand our understanding of what constitutes a typical icy body on a galactic scale. 3i Atlas illustrates how interstellar objects can carry traces of their long journeys. The refinement of internal structures over extended periods, the preservation of deep conduits, and the evolution of surface layers under cosmic radiation all contribute to an object that behaves differently from local comets. Yet these differences still fall within the broad framework of known physics. They simply represent combinations of conditions that are rare for objects formed in the solar system. At the same time, the precision and stability of the observed features raise questions about how frequently such configurations occur. If most interstellar bodies share similar origins or long-term evolutionary paths, then objects like 3i Atlas might be more common than current observations suggest. If, however, it represents a more unusual case, shaped by rare conditions, then each such object offers a unique opportunity to study processes not easily reproduced in laboratory or observational settings. Either interpretation highlights the value of continued monitoring. As 3i Atlas travels farther from the Sun and its activity declines, the persistence or fading of the linear jets will provide further insight into the durability of the internal structures. If the jets remain aligned even at low activity levels, it will reinforce the idea that the internal conduits are deeply embedded and structurally robust. If they fade quickly, it may suggest that certain conditions near perihelion were necessary for their formation. With these broader implications in mind, the next part explores how the behavior of 3i Atlas fits into the growing body of data from previous interstellar visitors, and what comparisons can reveal about the diversity and common patterns of objects traveling between stars. As the analysis of 3i Atlas expands, it becomes increasingly valuable to compare its behavior with earlier interstellar visitors. Although only a few have been observed, each case carries distinct traits that help define the range of physical characteristics expected from objects traveling between stars. Studying these similarities and differences provides a broader context for interpreting the unusual features seen on and after 17 November. The first recorded interstellar visitor displayed a strongly elongated shape and a brightness pattern that suggested rapid rotation. Its lack of detectable outgassing raised questions about its surface composition and internal structure. The second interstellar object behaved more like a traditional comet, showing significant activity as it approached the Sun. It produced jets, a visible coma, and a tail that aligned with familiar cometary patterns. These two examples immediately demonstrated that interstellar bodies can differ drastically from one another, suggesting a wide diversity of formation environments. 3i Atlas adds a new dimension to this picture. Its combination of stable linear jets, unusual composition, persistent non-gravitational acceleration, and distinctive polarization does not match either of the earlier cases. Instead, it occupies a middle ground, sharing some properties with active comets while displaying features not previously documented. This reinforces the idea that interstellar objects represent a broad spectrum of physical types rather than a single category. One important comparison involves the level of activity. While the first interstellar object showed little to no outgassing and the second exhibited vigorous activity, 3i Atlas demonstrates an intermediate but highly organized form of activity. The linear jets indicate strong outflow, yet the overall coma remains more controlled and structured than in typical comets. This suggests that the internal configuration of interstellar bodies can vary not only in composition, but also in the way they channel and regulate energy release. Another comparison relates to the response to the solar environment. Earlier interstellar visitors displayed noticeable changes in brightness or trajectory as they interacted with sunlight, radiation pressure, and the solar wind. 3I Atlas behaves similarly in some respects, but the persistence of its aligned jets indicates a level of internal stability not seen before. This stability provides insight into the mechanical properties of the nucleus, implying that some interstellar objects may be more resilient than expected. The internal structure of 3I Atlas appears to be especially distinctive. While the first interstellar object showed indications of rigidity and low volatile content, and the second displayed classic sublimation behavior, the third combines elements of both. Its stable rotation, consistent acceleration, and long-lasting channels suggest an interior shaped by processes that preserve alignment over long periods. This blend of traits hints at evolutionary pathways that can produce nuclei with characteristics not represented in local comet populations. One factor that unites all known interstellar visitors is their exposure to long-term cosmic radiation. Over millions of years, this radiation can modify surface chemistry, produce hard crusts, and influence internal structures. However, the degree to which these effects manifest appears to vary widely. In 3I Atlas, radiation may have played an especially strong role, creating a more rigid and directional internal architecture. If this interpretation is correct, then some interstellar bodies may carry signatures of radiation processing that differ depending on the environments they passed through. Another aspect to consider is the role of rotational dynamics. The first interstellar visitor displayed an irregular tumbling pattern, suggesting that its internal structure lacked symmetry. The second rotated more predictably. 3I Atlas shows a stable rotation that supports the alignment of its jets. The differences among these cases show that interstellar objects can retain or lose rotational stability depending on their history, internal mass distribution, and interactions with external forces. When these comparisons are assembled, a wider pattern begins to emerge. Interstellar objects appear to represent a continuum shaped by diverse formation environments, evolutionary histories, and structural properties. 3I Atlas occupies a position on this continuum that emphasizes internal alignment and mechanical stability. Its behavior suggests that some interstellar bodies may develop complex internal systems capable of producing highly structured activity when they encounter a star. This observation has implications for future detections. If more interstellar objects are observed in the coming years, their properties may reveal further examples of strong internal alignment or unusual volatile compositions. Alternatively, some may display entirely different behavior, expanding the known diversity even further. Each new case will contribute to a more complete understanding of how planetary systems throughout the galaxy form and evolve. The precision of the jets in 3I Atlas also suggests that internal organization may be more common than previously assumed. If even a small percentage of interstellar objects possess aligned conduits or fracture systems, then similar phenomena may be observed again. This would provide additional evidence that 3I Atlas reflects not an isolated anomaly, but a broader category of interstellar evolution. What remains uncertain is the frequency with which such features develop. If the processes that sculpt the internal structure of 3I Atlas occur in only a limited set of environments, then objects like it may be rare. If these processes are widespread across certain star-forming regions, then aligned interstellar objects may be more common. Determining which interpretation is correct will depend on future observations and the accumulation of more data. With these comparisons in mind, the next part examines how the unique features of 3I Atlas could influence its future evolution, and whether its internal stability is likely to persist as it moves farther from the Sun. As 3I Atlas continues moving away from the Sun, its future evolution offers another opportunity to understand how its internal structure responds to changing conditions. The gradual decline in solar heating should reduce outgassing, allowing the internal system of conduits and reservoirs to transition from an active state back toward dormancy. Observing how this transition unfolds helps reveal the strengths and limits of the mechanisms responsible for the linear jets. As sunlight fades, the most immediate change is a reduction in the rate of sublimation. For typical comets, this reduction leads to a rapid weakening of visible jets, followed by a gradual dispersal of the coma. In many cases, once activity drops below a certain threshold, structural features in the coma vanish entirely. What makes 3I Atlas especially interesting is how its stable linear jets persist, even as the overall activity decreases. This persistence suggests that the pathways guiding the outflow remain functional even under lower pressure. The ability of the jets to maintain alignment during this phase implies that the conduits are not dependent on high internal pressure to retain their shape. Instead, they appear to be structurally robust, capable of maintaining orientation even as the flow weakens. This resilience highlights the strength of the internal framework, which continues to guide any residual outflow along the same paths that produced the long linear features earlier. A gradual reduction in brightness along the jets also provides information about the depth and distribution of the volatile reservoirs. As the supply of readily accessible material diminishes, deeper pockets may become responsible for the remaining outflow. These deeper sources take longer to respond to temperature changes, creating a delayed but consistent release. The presence of such reservoirs indicates that the nucleus holds significant stores of material in well-protected regions, consistent with a formation history involving extreme cold and long-term preservation. Another factor to consider is the stability of the rotation. As the level of outgassing declines, any torque produced by jets decreases as well. For some comets, changes in activity cause subtle shifts in rotation rate or orientation. If 3I Atlas were sensitive to such changes, variations in the alignment of the jets would appear as the forces acting on the nucleus weaken. However, the available observations show no noticeable deviation in the direction of the jets as activity declines. This suggests that the object's rotation is not strongly influenced by variations in outgassing, reinforcing the idea that its internal structure is balanced and symmetrical along key axes. The behavior of the coma during this cooling phase also offers clues. While the main body of the coma gradually becomes more diffuse, the jets remain distinct for longer. This contrast supports the idea that the jets originate from a tightly controlled system of channels, whereas the broader coma reflects irregular sublimation from surface layers. As the irregular regions deactivate more rapidly, the difference between the structured jets and the general coma becomes more pronounced. Another consideration is how the solar wind interacts with the weakening outflow. As activity drops, the influence of external forces becomes relatively stronger. For many comets, this leads to distortions in the tail and other structures. With 3I Atlas, the linear jets remain relatively unchanged, suggesting that their initial velocity and direction are sufficient to resist moderate external influences. This further indicates that even at low levels of activity, the jets retain enough momentum to maintain their shape. These observations imply that the internal conduits guiding the jets are anchored deeply within the nucleus, rather than being superficial features vulnerable to collapse. Their ability to operate across a wide range of temperatures and pressures suggests that they are part of a coherent internal network rather than isolated fractures. This network appears to support long-term stability, allowing the object to maintain organized outflow even as environmental conditions vary significantly. The persistence of the jets also has implications for the long-term trajectory of the object. If outgassing continues to provide even a small amount of consistent thrust, the non-gravitational acceleration may remain measurable. This would allow researchers to refine models of the object's internal structure by analyzing how the acceleration changes over time. If the acceleration remains steady, it suggests that the same conduits remain active. If it declines, it may indicate that the deeper reservoirs are becoming depleted or that the internal system is transitioning into dormancy. As the object moves farther from the Sun, the eventual fading of the jets will reveal how deeply rooted the internal structures are. If the jets disappear entirely but reappear sporadically as deeper layers cool unevenly, it may point to a complex hierarchy of reservoirs. If they fade smoothly and never return, it suggests a simpler configuration dominated by a limited number of channels. Either outcome will provide valuable information about the architecture of the nucleus. Observing this decline phase also helps identify whether the linear jets were a product of temporary conditions near perihelion or a long-term characteristic of the object. If the features remain stable at low activity, it strengthens the interpretation that they reflect permanent internal alignment. If they dissipate quickly, it may indicate that the extreme linear structures required a specific combination of temperature, pressure, and illumination. Overall, the behavior of 3I Atlas as it recedes from the Sun reinforces the idea that its internal structure is both precise and durable. The transition toward dormancy reveals how deeply the channels are embedded, how stable the rotation is, and how consistently the nucleus directs outflow. These insights help refine our understanding of interstellar objects as dynamic systems capable of retaining complex internal architecture across vast timescales. The next part considers how the extended observations of 3I Atlas contribute to broader models of cometary evolution and what they reveal about the range of physical processes that may operate in interstellar environments. As the long-term behavior of 3I Atlas becomes increasingly clear, the broader implications for cometary evolution come into focus. The extended observations do more than describe a single object's unusual activity. They expand the framework used to understand how icy bodies form, evolve, and behave when exposed to new environments. By comparing familiar patterns from solar system comets with the rare characteristics seen in interstellar visitors, a more complete picture of cometary diversity begins to emerge. The first major insight concerns the range of internal structures that cometary bodies can possess. For decades, most models assumed that nuclei consist of loosely bound material with irregular porosity and no strong directional features. This assumption worked well for typical comets whose activity reflects chaotic sublimation from a patchy evolving surface. The behavior of 3I Atlas challenges this simple view. Its stable, aligned jets suggest that at least some cometary bodies contain deep structural elements that persist across long periods of activity. This realization supports the idea that cometary interiors may be more varied than previously thought. Some objects may have internal conduits shaped during formation. Others may develop directional features as a result of long-term radiation exposure. 3I Atlas demonstrates that a nucleus can not only develop such features, but preserve them through significant changes in temperature and pressure. Another important contribution lies in the role of external forces. Traditional comet models emphasize the influence of the sun, solar wind, and radiation pressure on shaping jets and tails. While these factors remain essential, the behavior of 3I Atlas shows that internal mechanisms can dominate even when external forces vary. The persistence of its narrow jets throughout fluctuations in the solar wind indicates that internal architecture can outweigh environmental disturbances. This finding broadens the range of possible explanations for cometary morphology. A further insight involves the evolution of volatiles within interstellar objects. The high carbon dioxide content of 3I Atlas demonstrates that reservoirs of volatile material can remain stable over millions of years in interstellar space. This stability supports the idea that complex stratification can develop within a nucleus, with certain volatile layers preserved more effectively than others. Such stratification may influence not only activity near a star, but also long-term structural evolution as different materials respond to radiation, temperature changes, and internal pressure. The object's stable non-gravitational acceleration also adds to this understanding. It illustrates how directional outgassing can influence orbital motion in a sustained and measurable way. While similar effects have been observed in solar system comets, the consistency seen here highlights how internal alignment can produce a long-term thrust vector. This has implications for interpreting the trajectories of other interstellar objects, whose motions may reflect internal features rather than simple sublimation. From a modeling perspective, the case of 3I Atlas encourages a shift toward more flexible frameworks. Instead of assuming that cometary behavior must fit into a limited set of categories, models may need to account for a wider range of internal geometries, thermal responses, and evolutionary histories. This shift aligns with the increasing recognition that planetary systems across the galaxy can produce bodies with diverse properties. Interstellar objects provide a direct sampling of these variations. The stability of the linear jets also raises questions about the potential prevalence of similar features in other objects. If aligned internal structures are not rare, then future interstellar visitors may exhibit comparable behavior. The rarity of observations so far may be due to limited data rather than limited occurrence. As detection capabilities improve, more examples may come to light, revealing patterns that help identify the formation environments of interstellar bodies. The extended activity of 3I Atlas also serves as a reminder that cometary evolution does not stop once an object leaves its birthplace. Interstellar space, often viewed as static and empty, exerts continual influences that can shape the material properties of traveling bodies. Cosmic radiation, impacts from micrometeoroids, and long-term thermal cycling all contribute to internal restructuring. Over millions of years, these processes can carve channels, compact material, and stabilize fracture networks. The behavior seen in 3I Atlas may be the product of such long-duration evolution. At the same time, the object's response to solar heating provides insight into how ancient structures reawaken. Deep internal pathways can become active again once enough heat penetrates the nucleus. The persistence of alignment indicates that these structures remain functional even after long periods of dormancy. This resilience may be a defining characteristic of certain interstellar objects, especially those formed under extreme conditions. Finally, the ongoing study of 3I Atlas demonstrates the value of multi-epoch observations. Single snapshots capture only limited aspects of cometary behavior, while extended monitoring reveals patterns that unfold over time. The linear jets, stable acceleration, and unusual composition all became clearer through repeated observations. As future surveys increase in sensitivity and frequency, similar long-term data sets may become available for other interstellar objects, enabling more detailed comparisons. With these broad implications established, the next part turns toward an even more fundamental question: whether the combination of precision, stability, and alignment in 3I Atlas points purely to natural evolution, or whether it indicates a boundary where familiar cometary processes begin to reach their limits. As the full set of observations is considered together, an important question emerges: whether the behavior of 3I Atlas can be fully accommodated within the boundaries of natural cometary physics, or whether its characteristics approach the point where traditional models begin to lose explanatory power. This is not an argument for extraordinary interpretations, but a careful exploration of where known processes may reach their practical limits. One of the clearest signs of this boundary is the precision of the linear jets. While natural conduits can form within a nucleus, the ability to maintain a straight, narrow outflow over 1 million kilometers approaches the upper end of what is expected from natural sublimation. Small irregularities in internal pressure, volatile distribution, or rotation typically introduce curvature or variations in jet shape. Yet the jets observed on and after 17th of November remained exceptionally straight. Their stability suggests a system that minimizes these irregularities to an unusual degree. Another indication involves the consistency of the non-gravitational acceleration. Directional outgassing can produce measurable thrust, but it often varies as surface regions heat and cool. In many comets, this variability creates complex acceleration profiles that change from one rotation cycle to the next. For 3I Atlas, the measured acceleration remains remarkably stable, pointing in nearly the same direction across multiple observations. This suggests an internal configuration that produces outflow with minimal fluctuation, which is uncommon in naturally evolving nuclei. The unusual polarization signal adds another layer. While polarization anomalies are known in some comets, the values recorded for 3I Atlas fall at the extreme end of typical ranges. This implies dust grains with properties that differ from those commonly observed. The consistency of the polarization across the jets suggests that the dust originates from a well-defined and uniform reservoir, which again points toward a highly structured interior. These features do not violate any physical laws, but they do require a combination of factors that are rarely seen together. When several independent anomalies align in this way, the interpretation becomes more challenging. It is possible that 3I Atlas formed in an environment where these characteristics naturally developed. It is also possible that its long interstellar evolution refined its internal structure in ways that rarely occur in the solar system. But both explanations require conditions that must combine with considerable precision. This raises a broader question. How often do natural processes produce such precise configurations? The answer may depend on how diverse interstellar formation environments truly are. If certain regions of the galaxy favor the creation of highly organized icy bodies, then objects like 3I Atlas may not be rare in a galactic context. If such regions are uncommon, then the object may represent a narrow subset of interstellar bodies shaped by specific and unusual circumstances. Another boundary emerges when considering the stability of the internal conduits. Natural fracture networks tend to evolve over time as pressure, impacts, and temperature cycles reshape the nucleus. For a conduit system to maintain alignment over millions of years, it must be supported by a rigid or reinforced internal framework. Such frameworks are theoretically possible under extreme formation conditions, but their persistence through long interstellar journeys requires careful consideration. In addition, the coherence of the jets suggests that the material passing through these conduits experiences minimal dispersion. This implies not only directional alignment, but also a controlled particle environment. Most comets release dust and gas with wide variation in particle size and velocity. For 3I Atlas, the outflow appears more uniform. Achieving this level of consistency requires structural features within the nucleus that regulate flow in a natural but highly organized manner. These observations bring the discussion to an important turning point. The behavior of 3I Atlas fits within the broad range of possibilities allowed by physics, but it lies close to the boundary where natural explanations require exceptional precision. This does not imply anything beyond nature. Instead, it highlights the limits of our current understanding of how complex internal structures can develop and persist in icy bodies traveling through the galaxy. A key part of this boundary involves the interaction between internal mechanisms and external conditions. For the jets to maintain alignment, the internal conduits must remain stable while external forces vary. This level of resilience suggests a strongly integrated internal system. If typical cometary nuclei lie at one end of the spectrum with loose and irregular structures, then 3I Atlas may reside at the other end, shaped by uncommon but entirely natural conditions. The final step in understanding this boundary is to consider how the object might behave if monitored over even longer timescales. As activity declines, the persistence or disappearance of the linear jets will reveal whether the internal system remains stable under minimal heating. If the jets retain their alignment even at very low activity levels, it would demonstrate that the structural features responsible for them are deeply embedded and resistant to change. If they fade quickly, it may indicate that certain conditions near perihelion were necessary to activate the full system. In either case, 3I Atlas provides a valuable opportunity to study the outer limits of natural cometary behavior. Whether it represents a rare example of highly aligned internal architecture or a more common product of interstellar evolution. Its features mark a point where familiar models begin to stretch. Understanding this helps refine the framework for interpreting future interstellar visitors, whose properties may expand the spectrum even further. The detailed study of 3I Atlas provides not only a clearer picture of a single interstellar object, but also a foundation for how future observations should be approached. As detection capabilities improve and new visitors are identified, the insights gained from this case can guide the development of better observational strategies, more accurate models, and stronger expectations about what may be found. One of the clearest lessons is the value of early and coordinated monitoring. The unusual features of 3I Atlas became apparent only because multiple observers captured high-quality data soon after initial reports. Stacked exposures, repeated measurements, and independent confirmations allowed small patterns to emerge from the background noise. For future interstellar visitors, rapid collaboration among observatories will be essential. Features as faint and narrow as the million-kilometer jets would not have been recognized without this level of coordination. Another lesson involves the importance of long-term tracking. The behavior of 3I Atlas changed subtly as it moved along its path, and these changes provided crucial clues about its internal structure. Understanding the evolution of interstellar objects requires monitoring them across a broad range of distances. Early observations reveal the onset of activity, while later observations uncover how that activity declines. Both ends of this timeline are necessary to reconstruct the physical processes at work. The unusual stability of the linear jets observed on and after 17th of November also highlights the need to look for directional patterns that may otherwise be dismissed. In many comets, faint linear features are often attributed to random fluctuations or artifacts. The case of 3I Atlas shows that such structures may hold important information about the internal architecture of the nucleus. Future observations should therefore treat narrow, persistent features with greater attention, especially if they appear aligned or remain stable across multiple images. Spectroscopic data also played a key role. The composition of the dust and gas emitted by 3I Atlas helped identify deep reservoirs and provided evidence for an internal environment shaped by extreme cold. For future interstellar visitors, detailed spectroscopic analysis will be essential. The presence or absence of certain volatiles, the ratios between them, and the behavior of dust particles can all offer insight into the object's formation environment. Another strategy involves monitoring rotational behavior closely. For 3I Atlas, the stable rotation period supported the interpretation of aligned internal conduits. If future interstellar objects show irregular rotation or rapid precession, it may indicate different internal structures or evolutionary paths. Tracking rotation over time helps identify how strongly internal features influence the object's behavior. A broader implication concerns the diversity of interstellar bodies. With only a handful of examples observed so far, the range of possible structures is still largely unknown. 3I Atlas demonstrates that interstellar objects may carry highly organized internal systems capable of producing long, stable features. This raises the possibility that other visitors may display unique or unexpected behavior that does not fit traditional cometry models. Building flexible frameworks that allow for a broad spectrum of possibilities will enable more accurate interpretation of future observations. The linear jets of 3I Atlas also offer guidance on what kinds of deviations from typical cometary behavior should be considered meaningful. Features that persist across changes in illumination, solar wind conditions, and internal pressure indicate strong structural control. Observers should therefore pay close attention to any structures that remain stable despite environmental variability. Such features may provide insight into the object's internal mechanics and long-term evolution. Finally, the study of 3I Atlas highlights the importance of integrating multiple lines of evidence. No single observation can reveal the full nature of an interstellar body. The composition, acceleration, polarization, brightness evolution, jet structure, and rotational dynamics all contribute different pieces of the puzzle. Only by combining these pieces can a coherent interpretation emerge. This approach provides a template for analyzing future interstellar visitors. Taken together, the case of 3I Atlas demonstrates that interstellar objects may be far more complex than previously assumed. Their internal structures can remain stable for millions of years. Their volatiles can reflect extreme formation environments, and their behavior near a star can reveal deeply rooted features shaped across long evolutionary histories. While the object's characteristics remain within the boundaries of known physics, they expand those boundaries, showing how natural processes can produce outcomes that are precise, stable, and uncommon. As detection surveys become more sensitive, more interstellar objects will be found. Some may resemble comets from the solar system. Others may display properties as distinctive as those of 3I Atlas. Each new visitor will help complete the picture of how icy bodies evolve across the galaxy, providing snapshots of environments we cannot observe directly. The study of 3I Atlas therefore marks not an endpoint, but the beginning of a broader exploration. It shows how much can be learned from a single object and how much more remains to be discovered as new travelers from other stars pass through our region of space. Each one carries the potential to reveal another fragment of the galaxy's history, preserved within its structure and released only when warmed by the light of a nearby star.